Okay, so there was a clarification about the question about what the images mean. So right, I showed this heat map. Let's see. Okay, so let me. Yeah, so you should definitely go and play with it, and then you'll see better what it means. But the way this is right is explained here a bit how this is done. But what it means is hard to describe. But you know, the singular vectors, right? They are they have an entry for each dimension of the vector of 700 and something dimensions, right? So each entry corresponds to a pixel. So you can put them back as an image, right? They were put as a vector for the SVD, but you can put them back as an image. And then you can try to see what is it that these singular vectors are what information are they giving? These are not the coordinates of different drawn numbers. These are the bases in which you're projecting your numbers to, right? So you have all your numbers, all your pictures, and these are the basis elements of the vector space of dimension 5 on which you're projecting all of them. And they explain most of the variance. In machine learning, people sometimes call these features, and they try to view features, right? So this is, I think, the interpretation, right? So maybe they are a bit, one feature explains if you're a 1 or not, or if you're a 2 or not, or a 3. I mean, this sort of looks like a 3. This sort of, it's, you know, this becomes very non-math if you start trying to do these kinds of things. Right? Did I answer the question? And now the chat is gone because I started sharing, but yeah, okay. So there were, okay, yeah, okay, great. So let me put back the poll. Someone asked me about the connections with linear regression, which is a great question, and I realized that I answered it thinking I was sharing my screen, but I wasn't. So let me just very quick say again. So this looks a lot, I agree, like linear regression. It is, however, a bit different, right? The actual difference is that, okay, I mean, in more dimensions, maybe other differences, but even in 2 dimensions, there's some differences, which is that here we're interested in these errors, right? Of how far you are from the line. While in linear regression, right, it's about supervised learning. So given X, you want to predict Y. So the errors that you are interested in are the differences on the Y-axis. Maybe another way of saying this is that for PCA, you do not care at all about where these guys are. Like the axes don't matter, right? The way we say this in math is it's rotation invariant, right? That if the axes were like this, it would be everything exactly the same, right? While in linear regression, definitely wouldn't. It would give you different lines. But I agree that, and yeah, and so linear regression is viewed as a supervised learning thing, right? So given X, you want to predict Y, and you have other labels. While here, there's no meaning in X or Y. Okay, so I hope that answered the question in a clear way. So okay, so maybe let's review, because I got asked in the break. Let me just say again, right? There's 2 ways of thinking about about PCA, or truncated SVD and so on. But let's focus now on PCA, right? I can ask, I want to write this. I want to write my point as a shift plus something that where the coordinates that depend on actually my vector k are very small, right? As a d-dimensional thing. I can ask about optimizing over the subspace in which I'm projecting, or optimizing over the coordinates, right? And these we see from the SVD that these are just the 2 sides of the left or the right singular vectors of the matrix. Okay? And it would make a lot more sense when you try to see PCA the first time, you'd optimize over U. But actually, this idea of coordinates is very powerful, right? So what is the idea of the coordinates, right? As I said again, you take given data points, m data points, you make entry ij be the inner product between them. Now you have an m by m matrix, which means that each row and each column are indexed by an index from 1 to m, right? And so this means the leading eigenvectors are a vector of m dimensions, right? And now the way that you can view as writing this vector is each data point k you associate with you're going to write it, you're going to draw it in the plane, like in the image of Europe. And what you can do is you can just say on the first axis, I write the kth entry of the eigenvector v1. I write v1 of k, v2 of k, v3 of k, and so on. If you think this is exactly what we're doing here, right? Because these beta k's are exactly my coordinates, and they're just the columns of v. I mean, you like scaled by the sigma, but it's not so important. Okay. But now comes another idea. Right? So far, there hasn't been really many ideas. We just are interpreting things in different ways. But here's an idea. Sometimes, data sets are not naturally captured by linear structure, right? I mean, you might have things like this, right? Maybe your data set, I think I drew them at some point. Maybe your data set is not captured by linear structure, right? But you still want to do, some kind of unsupervised learning of it, or supervised learning. Maybe you want to cluster it, or you get that these are all cats, a few of these are cats, a few of these are dogs, and I ask you about something over here, right? I can ask all these sorts of questions, and somehow linear structure doesn't seem to be able to capture this. Right, and we said another way is to create new variables, right? So here I had x and y, and I could create new variables. But there's a nicer way of thinking about this, right? And this is the idea of kernels. And so I'll just describe it a bit because we're sort of in a setting where it's very easy to describe, but I won't do much math around it because, I mean, to do it properly, you need quite a bit of functional analysis, which I see very few of you have seen. But now that I take this other approach where I have data points, x1 through xm, right? It doesn't even matter where they are, right? And I say, I'm going to draw my matrix. Let me call it M. My matrix Mij, right? That's just the inner product of xi with xj. And now I do something about this matrix M. I take its leading eigenvectors or something, and these become my coordinates. But now the point is, I don't need to be linear when I define this, right? I can think of the inner product as if the inner product is very large, then it means that it's a measure of xi and xj being very similar. If the inner product is very small, then it's a measure of xi and xj being very assimilar, for example. But now I can take other measures, right? So in particular, I can define Mij as any function of xi, xj. Right? For some kernel, right? K is called a kernel. It's just a way of measuring similarity. Okay? And now, the point is that now with this, I have a lot of freedom. First of all, my points don't even need to be in Euclidean space. My points can be anything, right? They can be proteins, and K of one protein and another protein could be how many processes have been reported to have together or something like this. Okay? But in particular, even if they're in Euclidean points, there is sort of an intuition that I think should come if you look at some of these examples. If you believe there's some kind of manifold structure, differential geometry structure in your data, is that you should trust small distances a lot more than large distances, right? So the idea of manifold learning, I mean, I won't talk much about manifold learning, but the idea is that trust small distances, right? Think of differential geometry. Right? Distances are well approximated locally, but because locally it looks like an Euclidean space, but far away it doesn't. Trust the small distances more than large distances. Right? And so if you do this, you might come up with kernels that if the distance is very small, they say it's similar. If the distance is far away, they say it's similar. It doesn't really matter how far away it is. So you can come up with kernels that are, for example, trying to measure the, just connect to the closest neighbors. These are called the nearest neighbor kernels. You can come up with all sorts of different things. Okay, so here's one example of a kernel. It's a very popular kernel. Right, so example. Right, this is called the Gaussian kernel. Okay, the point is if the points are very close to one another, if they're distance on the scale of epsilon, then this will be large, close to 1. If they're far away, this will be 0. It doesn't matter if they're at distance 1 or 10. If epsilon is very small, it's just going to be 0. right? So it's exactly within this model of trust small distances but not large distances. Okay. But now comes another interesting thing. So remember what we wanted to do with PCA, right? It was the covariance matrix of something. So one natural thing that we could ask for, right, in order for us to be able to think about PCA and take like an SVD kind of approach and so on, it better be that this matrix has only non-negative eigenvalues, right? It's natural to ask for. Okay, let me just say, or it would be natural to ask that if I think of the matrix M, right? So let's recall M is an n by n matrix, right? Where Mij is equal to K Xi Xj. Okay, it's a natural thing to ask that M is only negative or non-negative eigenvalues, right? So this means that all, I assume we've seen this in linear algebra, but all eigenvalues of M are non-negative. Usually, I also mean that M is symmetric. But in this case, I mean, these kernels tend to be symmetric always, right? They're measuring some kind of similarity, which should be the same going both ways. Okay. So now comes another idea, which is if this is the case, if this is positive semi-definite, then I mean, if you go recall, the linear algebra you've learned, it means that I can write M in its Cholesky decomposition, right? This is called the Cholesky decomposition. Okay. In particular, okay, if I think of these column vectors, right? It means that in this particular case, K or Mij, right? So K of Xi Xj equals, right, Mij. This is just the inner product between two vectors. So effectively, when I do one of these kernels, if the matrix M is positive semi-definite, we call when this always happens for any choice of points, we say the kernel is positive semi-definite. Then actually, this is now just a covariance matrix of some other vectors. So it means that I'm really doing the same thing as truncated SVD or PCA, but in a new function of the vectors, right? Going from Xi to a new thing phi I, which are often called as features. Feature vector. Okay? And so I would need some functional analysis to do this, but there's now very interesting, like one can try to, a very natural question that arises is, for which kernels K do I have this? And is it true that if a kernel K is always positive semi-definite, is it true that actually there exists a function such that for any points Kxi Xj is always equal to the inner product between phi. There's a map phi such that yeah, maybe I should think about it this way. Right, in which this would be called a feature map. So I don't want to go over very much because the requirements that I would need to prove to understand when this happens and so on. I mean, they require more than what the prerequisites of the course. However, let me just mention, for those of you that want to look more into this, I should mention Mercer's theorem. And I'll put in the notes, I'll put one of under a section if you want to know more, and I'll point to this. So this is one theorem to look at. There is also this beautiful theorem called Bochner's theorem. I'll just state the theorem, just to convey how nice of a theorem it is, that says that when your kernel is specifically of this style, right, when your kernel is specifically of the style some function, right, some little k of the norm between xi minus xj, right, then there is a relationship between the kernel being positive semi-definite and the Fourier transform of that function. Right, there's this beautiful relationship. I'll put it in the notes as references if anyone wants to read more into it. And I mean, this all surrounds some form of functional analysis, Fourier analysis, and so on. Okay, but when you hear about things like the kernel tricks, sometimes they call it, and kernel methods in machine learning, this is really what it is about. Okay? And depending how much time we have in the end of the course, we might revisit this again. But for now, we would require too much mathematical technology to do. Okay? But that being said, the fact that if I have m points, I can write this m, I can do PCA of it, and this means that to each vector x I'm associating another vector phi, this should be clear, right? This we don't need any more mathematical technology. What we need is to argue that if this happens for all xi and xj, I can always have the same phi's picked, right? I don't need different phi's when I have different sets of vectors. That's what needs a bit more math technology. Okay, so any questions about this? I'm going to move now to something a bit different, but it comes motivated somewhat from this as well. Okay, if not, then I'll continue. So we're going to talk about graphs. Okay, so I view very much spectral graph theory as a version of this kernel PCA style of thing, right? And so a very particular kernel is when you just take the adjacency or the Laplacian of a graph. Okay, so we're basically going to look at an example. Okay, basically, let's look. Okay, let me be a bit imprecise, and then I'll be more precise. Let's look at an example. Right. And the idea is we build an M by a matrix where, say, we place in M. In M, we place a 1 if points are similar, and 0 if not. Right? And so basically this takes us to graph theory. Right? This will take us to graph theory. Okay, so now let's go do graph theory. And again, I mean, I'm sorry, but I'm going to change the notation for the notation that's used in graph theory. But it's clear that all I'm talking about the points that are, they're similar, they get connected. They have a 1, if not, they're not. And you'll see that it's exactly the same thing as what people do in graph theory. Okay, so basic objects. A graph has a set of nodes, right? So has a graph has a set V of nodes. Throughout, the size of V will be n, right? Not m, because I mean this is what people use in spectral graph theory. Okay, and the set of edges. E. Okay, so E is a subset of the choices of pairs of vertices. Okay, and the pair ij is an edge if I is connected to j. Okay, so now let's draw a picture, because after all, it's a graph, okay? Right, so I have node, say node V1, node 2, they're oftentimes called vertices 2, 3, and so on, and I have connections like this. Okay, maybe I shouldn't use, I can just use, right? So the edges are the lines, and the nodes are the vertices. Okay. Okay, so this is an example of a graph. Right, it has 1, 2, 3, 4, 5, 6, 7 on seven nodes. Okay, and so now we're going to try to understand this object. Okay, we're going to try to understand the graph. I mean, there's whole courses on graph theory. There's all sorts of things you can ask yourself. We're going to be interested in understanding if a data set comes from a graph, trying to do some form of unsupervised learning on it. Okay? Very much from the kind of intuition that we had before of like kernel methods and PCA and so on. Okay? So you can think of examples, right? They can be nodes. Nodes can be, say, users in a social network. Edges can be like friend links. Right? There's many examples. They can be, proteins. Proteins can be the vertices, the nodes, and edges can be interactions. Edge present if they interact, if proteins interact. They interact. Right? This is called it's called a social network. Oftentimes, I mean, or the graph of a social network. This is called a protein-protein interaction. Okay, and there's many examples, as you might imagine. Okay, I guess the point that's worth making is that there are graphs that are directed, right? Like if you look at Twitter, for example, right? This would be directed. Here, I'm looking at undirected graphs. Okay, so there's no such thing as they go from one. They if they are connected, they are connected. There's no right because we're looking at kernels that were symmetric. Okay, so this will be the objective study. We're going to get things from a network, and we want to try to understand it. We want to try to do unsupervised learning on it. Okay, so let's define objects. So let's define the adjacency matrix. So A is an adjacency matrix. Okay, this is an n by n matrix. Okay, and now as it defined, Aij is going to be 1 if I is connected to J, and 0 if not. Right, connected means, right, of course, I mean, I think it's obvious, but. Right. Okay, so now this is a bit like my kernel matrix, right? So the idea that we get from before is that leading eigenvectors of this object will tell me something about the graph, right? We should already have in mind, I mean, this hint or suggestion or I don't know, foresight. Foresight, the leading eigenvectors of A should tell me, will tell me something. Will tell me something about the network. Okay, this is sort of what will happen, right? And this is the basis of spectral graph theory, spectral clustering, all these things that maybe you've heard some of these words before, right? This is the key behind, like key idea behind spectral clustering, for example. Okay, so let me try to now, prove some theorems to convince you of this. Okay, so we're finally going to get to some theorems. Okay, so clearly there's an issue with this, which is that I kept saying that I wanted this matrix to be positive semi-definite, and of course here in the diagonal there is nothing, so it's not going to be positive semi-definite for sure, right? So there's that issue. So we should make this positive semi-definite, and one way that this is done is actually by taking something called the graph Laplacian. Okay, so I'm going to define the graph Laplacian, and then we're going to prove a few theorems about it. Okay, so let's take define another matrix. This is again an n by n diagonal matrix. Okay, and the entry dii is going to be equal to the degree of the node I. So this is equal to the number of neighbors of node I. Okay. The size of the set of J such that Ij is an edge. Okay, so now the graph Laplacian is this object. Okay, so alert. Right, we took minus a, so it will be smallest e vectors that will matter. Right, I swapped things here because I took minus a, but this is classical in this field, and I should keep it. Things work out much nicer in this notation. By smallest eigenvectors, of course, it's a gross abuse of notation. It means the eigenvectors associated with the smallest eigenvalues, of course. Okay, so first statement that this matrix is actually positive semi-definite. Okay, so let's prove this. Okay, proposition, right? This, so proof. Okay, so I claim, okay, maybe I won't prove it quite because I'm going to prove something, yeah, so I claim more. Let's write the proposition and then that will follow. So proposition, L defined this way is equal to, and this is actually maybe how one should define the graph Laplacian. Okay. Where EI is the ith canonical basis vector. Okay, so proof of this, I'm not sure. I think it's like you look at it and you see that this is the case, right? Because, if you think about this, the off-diagonal elements are clearly, right? So the off-diagonal elements are clearly the right ones, right? I mean, I'm not sure how to, yeah, like the proof is just you look at it. So maybe, is it clear to everyone? If it's clear to someone, please don't interrupt. But okay, maybe what I should say, let's think about what this matrix looks like. Yeah, maybe that's how maybe I should write that. Okay, what is this matrix? You go, let's say put entry I, entry J, entry I, and entry J. This is a matrix that has a 1, a -1, a 1, and a -1. Right, it's exactly what this object is. Okay, and now it's clear, right? Because how many, the a -1, so Lij, so for, okay, so now what you have to check, for I different than J, right? Lij can only be either 0 or 1. Either Ij is in the sum and it's 1, or it's not in the sum and it's 0, right? So Lij is exactly minus Aij, right? You get a -1 if they're connected, and you don't get anything if they're not. And for I equals to J, for any I, Lii is what? It's just counting how many times. It's just counting how many times this sum shows up with an I, right? So it's just the sum over all J such that J is connected to I of 1. right? So this is exactly the degree of I, so it's exactly the II. Okay. Now, of course, this matrix, each one of these matrices, right? Now, okay, so this is the proof. Now, each one of these matrices is, of course, so it's easy to see that EI minus EJ, I mean, it's a vector times a vector transpose. So, of course, its eigenvalues are bigger or equal than, is rank 1, right? And it's positive semi-definite. All eigenvalues are bigger or equal than 0. If you sum symmetric matrices that are positive semi-definite, if you sum matrices, positive semi-definite matrices, they are positive semi-definite, right? Thus, L, right, equals to this sum, right, for all, I should say for all I and J, well, regardless whether they are an edge or not. Turns out that this matrix says a lot about the graph, positive semi-definite. Okay, now here's what's really important about this matrix. Okay, so what's really important about the matrix is the following. So take X in Rn. Okay. Now let's take X transpose L X. So what is X in Rn, right? What is X in Rn is a value, like effectively what we're taking is a value, a real number for each node. Right? We're for each node we're taking a real number. For node k we're taking xk. And now let's look what this quadratic form is. Okay, so of course, because the matrix is positive semi-definite, of course we know that this is bigger or equal than 0. Right? But okay, this will come out by itself also. What is this equal to? It's equal to sum I, j, and h. Right? I can move the x transpose inside. Okay, but what is this? And so this is just a number. This is also just a number. The same number. So it's just that number squared. Right? In particular, this is a number. What number is it? Yeah, I should write. This is just xi minus xj. Right? And so is that. So all I have is xi. So immediately we see that it's bigger or equal than 0. But it tells us more. It tells us that, for a vector x, it tells us how much, like it's summing the squares of sort of some kind of derivative. When 2 points are close in the graph, it's taking the difference between them and squaring that and taking the sum of the squares of everything. And in fact, if you think of the classical Laplacian, if you think of the graph being the grid in whatever many dimensions, and you think of the classical Laplacian, and you think of these formulas that are used very much in differential equations of like integration by parts and so on, you deduce things that look exactly like this, like integrals of norms of gradients being the same thing as the quadratic forms on the Laplacian operator that you'd use in differential equations and physics and so on. That's where the name comes from. But what do we learn also immediately from here? Right? This is sort of, if you want to remember one thing about the graph Laplacian, this is it. This is more important than what actually the entries are. It is the matrix whose quadratic form gives you this. The fact that the entries are actually very simple to represent is an added bonus. This is really what this object is. Okay, so now let's order the eigenvalues of this object. Now, again, we did minus a, so now the more important eigenvalues became the smallest ones, not the largest ones, right? Because we took d minus a, right? So let's order them in a different way than we've been doing so far. sorry for, yeah, this field is hard to avoid this. Right, so attention, they are ordered differently. Look at the order. Okay. Because it's positive semi-definite, we know that this fella is bigger or equal than 0. But we know something else, right? Claim that we know that it actually is equal to 0. Why? Because just by this formula above, let's call this formula sharp, by sharp, if I take the vector of all ones, okay, so what do I mean by this? I mean vector of all ones. This is what? This is the sum of the differences between 1 and 1. So this is just 0. Right? Because, right, since L is positive semi-definite, right, then it must be actually that 1 is in the kernel, right? So then L1 is actually 0. Right? If you've never seen this kind of argument, just, because it's positive semi-definite, just take its scholastic decomposition, take its square root, right? Take L needs to be equal to QQ transpose, and then just, you see that, right? Right? L needs to be QQ transpose, which means Q1 needs to be 0, and so then when you plug it here, you get 0. Now, okay, so this means in particular that lambda 1 of L is 0. Okay, so there's one eigenvalue that's very boring. And we even know the first eigenvector, right? The eigenvector associated with it is the whole one's vector. I mean, maybe let's normalize it, but okay, I don't really care so much about normalizing things, right? I mean, it's not so important, but usually we tend to think of eigenvectors as having L2 norm 1. Okay, and now we can ask, right? So what about lambda 2 of L? Right, so can this be 0 too or not? So lambda 2, right, by the variational principle, which showed a bit in the lecture notes, and it will show up a few times also in the homework, right? I'm assuming you've seen some of this in linear algebra. This is 0, right? Basically, if and only if there exists a vector y that's orthogonal to the smallest eigenvector, right? To the eigenvector associated with 1, such that y transpose Ly is equal to 0. Okay? In other words, such that the sum over all I, j, and edge square is 0. But what does this tell us? Okay, so let me see if I can do this in 2 minutes. Right? Let's say that I have, okay, so this is the case. Okay, but let's say that we have this. Okay, so let's say W2 L is equal to 0. Let's assume. Okay, so I'm going to use now this equivalence to prove this equivalence is just statement in linear algebra. I'm going to use that equivalence to prove something. If W2L is 0, then there must exist such a y, right? And now this y, right? So let's assume W0 and take y as above, as in above. For sure, y needs to have positive and negative entries, right? Because y is orthogonal to 1, so it needs to both have positive and negative entries, right? It can't be 0, of course, right? I mean, I guess it's important, right? Y cannot be 0, right? Otherwise, this is vacuous, right? Take y as above. And now let's take a set S, subset of the nodes, right? And the way I'm going to define this set is the set of nodes such that yi is positive. Set of nodes I in V such that yi is positive. Okay. So first claim, S needs to not be equal to V, because otherwise the vector would all be positive, could not possibly be orthogonal to hole 1, and it cannot be empty, because otherwise S would be, otherwise the vector Y would be non-negative. There's no way it could be orthogonal to the hole 1's vector. Okay. However, if W2L is 0, then I must have that the sum of ij edge yi minus yj squared is equal to 0. But if, I and j. But if there's a term in which I pick up one positive number and one non-negative number, then this term must be bigger or equal than 0, right? So because all these terms are positive, this implies in particular that for all I connected to j, yi needs to be equal to ij. Right? So this means in particular that no element, no vertex in S is connected to a vertex in S complement, like right outside of S. Right? Because otherwise, I grab the edge, right? If there was I in S and J in S complement, such that I is connected to J, then, right, yi minus yj squared would need to be strictly positive, and this would be a contradiction. So this means that the graph must be, there must be something going on here, something going on here, S as complement, and it must be disconnected. So this means graph is disconnected. Okay, so there is a set that is not connected in any form to the rest of the set. Okay. Now, on the other hand, if the graph, okay, so now it should be clear also that if the graph is disconnected, right, if G is disconnected, right, then take S and S complement, don't have connecting edges, right, then it's kind of clear that you can pick Y to be a number in S and another number in S complement and make it orthogonal. So we're going to do this next week. But basically the theorem that essentially is proved already, I'll do the rest next week, is lambda 2 of L equals to 0 if and only if G, the graph G, is disconnected. Okay, so next week, sorry for taking a couple more minutes. Next week, we're going to finish the proof of this, but we're going to do a soft version of this. Right, we'll do a soft version. Right, so, compare what if G is almost disconnected, does this mean that eigenvalue need to be small? Or if the eigenvalue is small, does it mean that the graph needs to be almost disconnected? Okay, sorry for taking 3 extra minutes. I'm happy to stick around if there's any questions.